Welcome, ladies and gentlemen. This is our final video in our gases unit, video number 5. In this video, I'm going to be wrapping up a few what I would consider sort of smallish topics, just a few final things to discuss. They are something called partial pressure, and then effusion and diffusion. So partial pressure, first up, the definition of partial pressure is the fact that if you have a mixture of gases like air, and you combine them all together, a partial pressure is what is the pressure of just one individual gas. So it'd be like saying in air, which might have some sort of total pressure, how much pressure is just the nitrogen exerting, or how much pressure is just the carbon dioxide exerting. So what is the pressure that just one individual gas in a mixture is giving off? And Dalton's law of partial pressure, how we use this, I think it's fairly intuitive. If you have a mixture of gases and each one is exerting their own individual pressure, if you simply add them all together, add all those individual pressures together, you do in fact get the total pressure of the system, which I think should make sense, right? If one gas has a pressure of 1 atmosphere and another gas has a pressure of 0.3 atmospheres, and you put them together, then altogether you're going to have a pressure of 1.3 atmospheres. And Dalton's law of partial pressure says exactly that. So P total, so the total pressure is equal to P1, so that would be a partial pressure of one thing plus a partial pressure of a second thing plus a third thing, etc., adding it all together for the whole. Now this picture right here, this is sort of showing this idea. So in this first canister we have hydrogen, in the second canister we have helium, and in the third one we have hydrogen and helium together. So this is our mixture of gases. The first canister has a pressure of 2.9 atmospheres. The second one has a pressure of 7.2 atmospheres. And the third one has a pressure of 10.1 atmospheres. Well, where is that 10.1 coming from? Well, all we've done is we've added together the 2.9 from the first one plus the 7.2 from the second one, and that gives us the 10.1 of the third one. So it's just showing that partial pressure of one thing plus partial pressure of something else is equal to the total pressure of the system. So just an example with that, determine the total pressure of a gaseous mixture that contains oxygen, nitrogen, and helium. And then it says the partial pressures are, the partial pressure of oxygen is 20 kilopascals, the partial pressure of nitrogen is 46.7 kilopascals, and the partial pressure of helium is 26.7 kilopascals. And we want the total pressure, so P total. Well, all we're going to do in this case is simply sum them all together, right? If we add all the individual partial pressures together, we're going to get the total of the pressure of the system. So summing together all the individual pressures, we can then get the total pressure of 93.4 kilopascals. So that's all we need to do for partial pressures. Sum them together to get the total pressure of the system. Next up, diffusion. Diffusion is something you should have seen before. You've probably seen this in living environment. You talk about diffusion maybe of like water over a membrane. Osmosis is an example of that. Particles will always move from areas of high concentration to areas of low concentration. And I know you've seen this before, because if someone farts in one corner of the room, eventually another corner of the room you can smell the fart. So what's happened is that the gas particles that were given off by someone, they moved from the area of high concentration where they were given off, and then they spread out to areas of low concentration, other sides of the room, right? Odors spreading across the room. This is an example of diffusion. Effusion is a similar idea to diffusion in terms of, they're both in terms of gas particles moving, but effusion is the fact that gas will escape its container through tiny holes in the substance, so that even if you were to put gas in some sort of container, it will always find a way out, even if it's like a big steel thing. Over time, the gas will find its way out. And you have all seen examples of effusion before, whether or not you've realized it was effusion. And where you've probably seen effusion is the fact that balloons will eventually deflate even if you don't pop them. And the reason that the balloons eventually deflate is the gas particles that are inside the balloon, they find tiny, like microscopic holes in the container and they find their way out. Now the holes are really small, which is why the balloon doesn't deflate right at once. This is why it takes like months for the balloon to deflate, but the holes are there and the gas particles will find them and they will actually leave. And the thing with both effusion and diffusion that we need to know is that smaller particles will both effuse and diffuse faster than large particles. Basically, small things, small gases, will move at a higher velocity, can spread out faster, and can find their way out of the holes faster. Now, as always, we talk about small versus large in terms of GFM. So this is our fastest way to figure out if something is small or big. What is its gram formula mass? Is its GFM small or is its GFM big? So, and we can use that to compare. So for example, helium, which has an atomic mass of 4 AMU, or 4 grams per mole, will both diffuse and effuse faster than carbon dioxide, which has a GFM of 44. So because that 4 for helium is smaller than the 44, the helium is going to be both effusing and diffusing faster. So just as an example, which will effuse faster, neon or oxygen? Well, again, we're looking up gram formula masses. Right now with the O2, now remember, you've got to double the oxygen, so we're not going to do 16, we're actually going to do 32. So neon is going to effuse faster because neon's mass is smaller, 20.2 AMU versus 32 AMU. So neon is going to effuse faster. It will also diffuse faster. So the small things are being faster in both cases. And then this one, which will diffuse more slowly, chlorine or hydrogen. Well, notice in this question I didn't ask which one was faster. I asked which one was slower. So now we want to go with the larger gas, right, for the slower one. So again, we're looking up GFMs. So chlorine, because its gram formula mass is 71, it's going to diffuse more slowly than hydrogen, which is just 2, right? Hydrogen and helium, those are very, very small gases. So they're going to move more quickly. They're going to both diffuse and effuse a lot faster.